outside I posted the solution that we developed in class, plus some additional code for fold, which is also called use, and an exercise in math that you might want to do in preparation for this upcoming assignment where you're going to be using higher functions, fold, map, and for each thing to do different things. Any questions about that? Okay, so we come to the very last piece of C and Java and other languages we haven't discussed yet, switch statements, and to the an additional use of function pointers. And so it might surprise you that function pointers are used in switch statements. It's not obvious, it's not explicit, but they are used in the implementation of some switch statements to make them execute faster. To see why, let's look at a switch statement, slightly different than the one that's up there. So you switch on some expression that evaluates to what I just call I here. And then say maybe case 10, and then there's some code, a break, case 11, same thing, case. Let's skip 12, 13, same thing, and then maybe default. And then switch statement. Now, if you were developing a compiler to compile this, like we looked at for loops and if statements, you might translate this into some more basic thing as a way to see how eventually you produce the machine code. And any switch statement can be transformed into a set of if statements. So you can say if I equals 10, then do this, else if I is 11, else if I is 13, else. Right? So you can do that. And in fact, you could just write this code instead of switch statements. So why do you think that programming languages have switch statements in them? What's the point of switch statements? Any switch statement can be written with this. Who likes switch statements? Come again. So you don't have to write this, but what's bad about this? What's better about the one on the right? Well, there is. So we're gonna talk about how it's possible to generate code that will execute faster than the code on the left. But I don't think that's why you have thought about it. That is one reason.
Just in the code itself, it's a lot easier to read. It's a lot the cases are really equal.
Yeah, it's easier to read. And so a key thing here is that the switch statement is more restricted than an if statement. Well, every if statement can be implemented by a switch statement. Every if statement can be implemented by a switch statement, at least not in an obvious way. So this is sort of more general form of control flow. This is a very specific one that is designed to match a common idiom in programming. It's common that you'll have some value that you compute, and then you use that value to choose one of a set of different things to execute. You've seen this in the simulator, right? So the CPU.java execute procedure has a switch statement that switches on opcode, right? And executing an instruction, that opcode chooses which instruction implementation to execute. Same thing actually happens when Java programs themselves are being executed by the Java virtual machine. The Java virtual machine is a gigantic switch. It's a loop and a gigantic switch statement. And that switch statement is switching off the Java bytecode opcode that then selects a piece of code, C code, to execute that does that thing. Now, eventually Java programs will be compiled down to machine code as they execute, so that piece goes away. But that's another example. And in both of those examples, actually, the performance of the switch statement matters too. Because it's inside a loop. It's, you know, and it's also potentially a big switch statement. Okay, so switch statements are nice because they provide this matching of structure that's reduced in complexity to a common programming idiom. Therefore, it's easier, the structure is easy to see, it's easier to read and possibly also write switch statements. The only thing I would say about them, there was one mistake that was made, it was carried through every programming language, which is break. So it's actually also easy to write switch statements with bugs because you forget to put the break in. That happens a lot. But that's a completely separate issue. So, you know, if you believe, and I think everyone certainly is, already knew that this is somehow better than this. And so when you have an idiom like that, you kind of write it like this. Why isn't it the case that in C and C++ you can't have switch statements like the two on the bottom? You can't switch on a string, or you can't switch on, say, two variables, or you can't switch on inequality. All of those things are things that you might want to do that sort of fit that same idiom. But it's only a few languages. Java, starting in version 8, you could do some things like this, where you're allowed to do that. Mostly in languages you couldn't. In most languages, C, C++, and pretty much everything until the modern days, and changes to Java, this had to be countable. It had to be basically a number or something with map on an integer or map onto the integers. Why is that? Has anybody ever wanted to write a switch statement like this one? Like, for example, let's say you were writing the Java simulator, you actually could have done this, and rather than switching on opcode numbers, maybe you could switch on opcode strings. And your switch statement would be easier to read because you have the string, load immediate, colon, case, load immediate, and case, load base offset. Oh, it's so beautiful and easy to read. Right? And you can do that in Java. We'll talk at the end of this part of the lecture. We can come back and consider the question, is it a good idea to do that? Why is it like this? Why are those things not allowed? Let's see. Any idea? If you had a super long string, you know what would happen. Well, if I implement it like this, it's perfectly fine. But the reason those things aren't allowed, the reason that the restriction exists, that this must be countable, is so that the implementation strategy I'm going to explain now is possible. So one way to compile this code is like that. But another way is to do the following thing, is to use a jump table, where there's an entry for every case that's listed here, and I'm going to use a normalized value of the case label as an index into the table. So you find the one that's the smallest, which is 10. And that's going to become index 0. And the jump table, so we've seen jump tables before pointing to procedures. These are function pointers. But now they're going to point, rather than to a procedure, just to this block of code. So it points here. And then this break will be a go-to. And then case 11, same thing. That'll point to this code. Case 12, there is no case 12. So where should that point? What happens when I is 12? Default. So that should point to the default case. And case 13 here. And then everything is smaller than the lowest case label or bigger than the biggest case that won't be handled. having done that, now what we can do is generate the following code. So I'm going to take I and normalize it by subtracting the lowest level, case level. So I get this temporary variable t will be an index into this table. So I'll say t equals I, in this case minus 10. That minus 10 is this. And now I have to check array bounds. So I say if t is smaller than 0, or it's bigger than, well, what's the biggest index? 0, 1, 2, 3. Then I should do something. What should I do here? Well, what should happen if I is, say, 9? Put the default. If I is 20. Put the default. Right? So if I is 9, then I subtract it and get minus 1. Minus 1 is less than 0. If I is 20, I subtract it and I get 10. 10 is bigger than 3. So in either of those cases, I'm just going to go to default. And then in every other case, I'm going to use the jump table. So let's call this thing, this array, JT. So that's an array of pointers. I'll just go to JT. So in this one step, I'm choosing one of these decks. So if we were to compare, using your 221 knowledge, the asymptotic running time of this implementation compared to this implementation, where n is the total number of case labels. What is this? Big O of what? O of 1. What is this? O of n. What's better? O of 1. Right? So this is really cool, and it's using the idea of the index. That's how we're getting, the index now is going to pick from this big array which element of the array points to the code to execute. So I don't have to compare I to each of the possible values. It's almost a little bit like a hash map. Think about it. Just take that number and you go straight to the place you want. Okay, but the compiler doesn't always use this strategy. There are situations in which this strategy would be a really bad idea. Can anybody think of what one of them might be?
By a lot.
Right, a very sparse switch statement. For example, here's like a really bad one. That's a billion. Why is this bad? Well, it's bad because the size of the jump table ending. So how big of a jump table is required if I use the technique on the It has to have a billion entries. So the first entry here, I'm going to normalize by subtracting 1, so that this will correspond to case label. Index 0 is case label 1. So then I've got to go all the way down here to number 9, index 999,999,999, and this is for 1 billion. And I can't skip any in between because it is the fact that I'm just going to use I, whatever I is, subtracting in this case 1, as an index into the table is what gives us the over 1 performance. So it's a direct trade-off. The table has to be that size. So if we were to describe now what determines the size of the jump table. And think of this as, so here we have time complexity, O1 versus O(n). That is the same in this other case, but we also consider space complexity, the asymptotic size that's needed to implement this. So what determines the size of the jump table?
Largest size, subtract.
It's the difference between the largest case label and the smallest case label, plus 1. Right? So this is size O of large minus small. What is the space complexity of this? Okay. So, when the difference between the largest and the smallest case labels is significantly larger than n, then it's better to do this. But what you give up is time complexity. Right? As soon as you switch over to this, now you have O of n running time, but you can also have O of n size. Over here, you have O of 1 running time all the time, but you might have ridiculous size. And so what does the compiler do? Well, the compiler looks at the switch statement and uses some heuristics to decide which of these two implementations to use. In some cases, it's completely obvious. So, for example, if you only have one case label, you might as well do this. It only really matters. You only get a benefit of O1 versus O of n, where n is big. So if n is small, it doesn't matter. Okay. If n is reasonably large, and the case labels are densely packed, quite obvious to use this one. And of course, in the case where they're very, very sparsely packed, it's obvious you use the if statement. But there's a place in between where it is not so obvious. Right? The compiler is going to make a choice. And it actually could matter to the programmer that space matters more than time, or time matters more than space. So if you're like writing some code that's going to be inside of a light switch, well, here space really matters. You have a very limited amount of storage there, but maybe time doesn't matter. On the other hand, if you're compiling code to run on a big machine that's got lots of memory, and you're writing code that needs to run fast, you might be willing to sacrifice some space in order to get the time. And so for this reason, when you compile C program, C++, you can specify whether you prefer to optimize for space or for time. And the compiler uses that as one of the heuristics that it'll use to choose which technique to use. But now let's come back to this idea of using strings in Java. So let's say you do that. Let's say that you write your Java simulator for SM213 so that you use strings. And we're going to add a lot of other instructions to this. So we have a full-fledged ISA. So the switch statement is much bigger. You do it with strings, I do it with numbers. Your code is beautiful, mine is ugly. It's just case 0, case 1, case 2, hard, terrible. Yours is beautiful, everyone loves it. Except, mine runs much faster. Why can't the compiler take your code with the strings and use this technique? So how many strings are there between quote A and quote B? Infinite number, right? So what's required here is to map from the labels onto numbers, because the number is going to be indexed into the table. So if you just have strings, there's no obvious way to do this. In fact, this is what a hash map is. You compute a hash, and then use the hash. But just computing the hash, that was going to slow you down. I mean, maybe that would make sense, actually, in some really, really big cases. But makes much more sense to just know this as a programmer, that if performance matters, use numbers, even in Java. In C and C++, you have absolutely no choice. But now my code is so ugly. I say case 0, case 1, case 2. Yours was so beautiful. You said case low to medium. How do I make my code better without losing performance? Constants, yes. What you should do is define constants. Some languages have something called an enum. Like Java has this. That is a named typed constant. If you don't have that, just create constants. And then you can say case, capital letters with underscores, low to medium. But it's really just a number. Another thing to keep in mind is when you pick these numbers, if you can pick them, sometimes the numbers are represent something in the outside world and you can't choose them. But if you pick them, don't pick numbers like, okay, well, I'm going to save a lot of space in between. So I'm going to have like 1,000, 2,000, 3,000, 4,000. Don't do that, because that's going to either require a really big jump table, because you're going to have 999 useless entries between each of them, or it's going to force the compiler to remove statements. So this is an example of thinking below the abstraction a little bit to know that the way that you structure the switch statement might affect its performance in a big way. Now, sometimes it doesn't matter, but if you've got the loop that executes a lot, and inside the loops, the switch statement in a lot of cases, then it probably doesn't matter. Okay. Questions about that? Okay, so the slides have a bunch of stuff here that I've covered. Oh, I didn't show you this. This is a good picture of what's happening. The first box here doesn't normalize, because in this case it starts at 0. But the one if statement that checks the array bounds and goes to default. And then the next thing is the go to, and ignore the syntax for just a second, I'll explain that. And that goes directly to one of the cases. And then when they're all done, they all go to the end. So each of those green lines is a single jump. And that's how we go on performance. Now, a little bit on syntax. So what I wrote here describes what would happen. And if I just went straight from this to assembly language, this is like pseudocode. It'd be perfectly fine. But actually, I can describe this in C code and execute it, which is what we've done with ifs and loops, and it's what you're going to be doing in the assignment. In the assignment, you're going to re-implement the entire simulator in C. It's actually true, but we're going to do it part of it, and it won't have a loop. And then you're going to take the switch statement and change it into not using switch, but using jump tables directly. So if you want to program in C with jump tables, there's this very strange bit of syntax you have to do. So that's what it's on the right-hand side. So first of all, the JT, first line, JT is the declaration of an array of 4 things that are just said their type is void star. Okay, pointer could be pointer to anything. But this is it's like a function pointer, but it doesn't point to a function, it just points to an arbitrary chunk of code. And then the weird thing is that, before I get to that, you see the labels declared next to the code. L0 is the code for the first case, L1 colon, the second case, and so on. And the jump table needs to store pointers to those things. And you get the pointer by saying ampersand, ampersand, labels. Now, if there was just one ampersand there, it kind of makes sense because it's the address of the label. And it will be actually whatever that code, wherever that, say that's at the memory address of the first line of this code is say 3000. It would be the number 3000. It's just the address of the first line of that code. But for reasons I don't want to go into, but I'll very briefly explain. I don't want anyone to ask questions. You need 2 ampersands. And it doesn't mean it's like the address of the address. There's no significance at all to there being 2 ampersands. The reason that there's 2 is just simply there's a problem if you only have one, is that the namespace for labels and the namespace for variables are different. So I can have in the same scope a variable that's named L0 and a label that's named L0. And until you do this, the compiler can distinguish them by context. You can never use a label in syntax where it expects a variable. You can never use a variable in syntax where it expects a label. Right? Labels are just label colon and go to label. That's it. You can't have variables there. And so now, if I just put an ampersand there, this would be a situation where you could have either of those. And to get around that ambiguity, it was just totally arbitrarily chosen to have two ampersands. It's just weird. Okay, but you have to do it that way. And then the third line is the indirect jump version of the go-to. So that's a double indirect jump actually. So you say go to star, just like, remember the double indirect jump, just like this. Right, the address that you jump to is in memory, and at that address. And here, the address is in memory at that location in the internet. Okay. So, I don't know, just a little bit of weird syntax, and you'll need this when you do this. Okay. Questions? All right, so the rest of this, I just got one more thing I want to show you. It's just all stuff that we've talked about. You might want to take a look at it. It's just the following thing. So you haven't seen this before. This is the syntax that combines arrays and function pointers. So it's possible to have an array of function pointers. If you look at the fourth line, that declares the variable proc to be an array, three things, and each of them is a function pointer. And so and it accepts functions that don't return anything and have a single integer parameter. And if you look at the other bold line, which is the last one, if you want to call a procedure that one of the elements of proc points to, then you combine the array syntax and the function syntax like that. You have to use the array syntax to select each one, and then the function call syntax to call it. Questions about that? Okay, so we're ready to move on to the second unit of the course. We'll be doing something quite different. Here's the learning goals. Here's the so for the last 7 weeks, we've taken a very simple model of execution that has a CPU executing a program with no operating system, just a single program in the CPU, and a main memory. And we developed an instruction set architecture that's Turing complete. Any program can be compiled into it, that when the program runs, it interacts with data that's in memory. And while this is Turing complete, they're extremely boring programs, because these programs cannot interact with the outside world anyway. So we want to change that now. So we're going to change that by adding I/O devices to the machine. And we're going to talk today, the rest of today, about how a program running on the CPU could interact with those I/O devices. A lot of the stuff we're going to talk about here would be stuff that's actually in the operating system. We're just going to look at it as basic mechanisms since we don't have an operating system. Okay, and then we'll continue this next few weeks. So this is the picture. So I've got CPU memory as before, and then the purple boxes here are I/O devices. So let's give me some examples of an I/O device. Mouse. Touch screen. Radio. Don't read all this. I mean, come on. More examples.
Keyboard.
Keyboard. It's lunchtime. Nobody wants to think. Come on.
Screen.
Gyroscope. Very good. Yeah, absolutely, yeah. Maybe. Some things, something like a gyroscope, so you can detect the orientation of it. What else? Accelerometer. Great. Absolutely. So you can see, so Apple can tell if you drop your phone, so they won't refund your money if you break these with your screen. What else? There's some really basic ones you haven't mentioned.
Screen.
A screen, yeah.
Speakers.
Hard drive, yeah, so storage. There's all kinds of different secondary storage devices you might want, USB dongles and other kinds of storage disks, and VRAM. And there's another one. But without this particular one, I don't think any of you would you've ever used a computer. No, not monitor, not screen. Network, yeah, right. So it's network. And a bunch of other ones, you know, there's a thing that makes your phone vibrate, there's sound and all kinds of things. So, those are all the purple boxes, and each one of them is idiosyncratic to a certain kind of interaction, right? So, the network might be Wi-Fi, so it has a radio receiver transmitter. The haptic devices have, you know, the things that can vibrate, or things that has a speaker. The mouse has got trackball, clickers on it, the touchpad has got some kind of a screen, has some kind of capacitive touch recognizing thing. Gyroscopes have some, you know, they all have some specific, you know, weird thing that's used to interact with the outside world. And they all have on them a small processor. And we call that processor the I/O controller. Those are the blue boxes. The I/O controller runs a small program. Sometimes it's very, very simple, just like a state machine. It doesn't even have to be a full-fledged CPU. And the role of that program is to handle the interface between the I/O device and the rest of the system. So sometimes these controllers are, sometimes they're called interfaces too, an I/O interface. Okay. And the way I want you to think about these things is as processors. So we can take a look. You take a look at, you know, what's circled in orange, and you see what we have is a network of processors. Now, they're not all CPUs. The blue ones are very, very simple processors, but they're all processors. And so now, this problem, which we're going to talk about, which is how do they communicate with each other, really generalizes to processors connected by a network. I mean, you can imagine this being something like the internet, or multiple CPUs trying to talk to each other, say in a big multiprocessor computer, or anything like that. It really is just the problem of multiple processors running independently of each other, communicating over a network. Now, in this case, so we're going to focus on, well, we're going to discuss that issue in general. That's sort of the main theme of the rest of the course. But first, by focusing on the specific characteristics of this particular interaction. And we're going to look at three mechanisms that are used, that are built into hardware to do this today. All of them operate through a bus that each of the controllers is connected to. And the controllers are programmed to understand the protocol on the bus that implements the things we're going to talk about, as is the CPU. So, first thing, most basic things, I want to write into a program the ability to communicate with an I/O controller, to send it a message, and to receive a message from it. In this case, we'll just start with messages that are a single word. You know, could be a quad, so 8 bytes, could be a long 4 bytes, something like this. Okay, single word, back and forth. And the question is, how do we do this? So right now on the CPU, so I have a program, and the program needs to do this, and the program's written in machine code. And in our ISA right now, we have 3 kinds of instructions. We have instructions that do math, with the control flow instructions that do jumping and branching, and then we have instructions that access memory, loads and stores. So what we could do is add a fourth kind of instruction that was designed to communicate with I/O controllers. But we're lazy. We don't want to have to add, we're done. Like, we're done with the ISA. I don't want to have to add anything more to the ISA, but I can avoid it. So is there a hack that lets me keep the ISA exactly as it is and use the load and store instructions to communicate with an I/O device? And the answer is yes, there is a hack. I don't want to call it a hack, but sort of like that, sort of like. And the idea here is that we're going to use the memory address space of the machine to refer not just to memory, but also to I/O devices. So we'll have the regular part of memory we already had. Right? So this is, here's memory. And it goes from address 0 to n minus 1, where n is the size of memory, number of bytes in the memory. Okay? But imagine that isn't the end of all possible addresses. Right? So if I have a 64-bit address space, n will be much smaller than the biggest number that you can have. 2 to the 64 is like a massive number. No one could ever afford to buy that much memory. In fact, I don't even know if that much memory exists in the universe. So there's a certain point where this stops, and we can take, and if you access an address that's bigger than n minus 1, that's just a hardware failure. It's like that memory does not exist. So you could try to load or store and just the illegal address, and your program crashes. We're going to change that, so we'll take some of those addresses. So we'll just say it goes from n plus k minus 1. It doesn't, the details don't matter. That just some of the addresses that used to be illegal, and we're going to make them legal, and we're going to assign them to the I/O controllers. So that if I want to send a message to an I/O controller, I will do a load or a store to its I/O address. You can see in this picture, we've assigned the addresses to each of the I/O controllers sort of in ranges. So the first one is 800 and 800FF. The next one would be 800 100 1FF, 200 2FF, 30. So they're non-overlapping. And the bus knows which one has which address. And when things connect to the bus, the bus controller gives them an address. Okay? And the operating system will also know the addresses. So if I want to send a message to the first controller, I can just load that address, 8000 into register 0, put whatever message I want to send into register 1, and do a store. And that store will send a message over the bus to that location. So if I store to a regular address, it goes to memory. But if I store to one of these other ones, it doesn't go to memory at all, it goes to our controller. And it's not like there's memory out of the controller, it's not memory at all, it's just a trick. So we can send messages to the controller. Same thing if I want to get data back, I do a load. Now a load will send a message down to the controller with a request, and then the load will wait for the answer to come back. And that takes a long time. It takes a long time because these I/O controllers are very, very simple processors. They cost like a nickel. And the CPU, on the other hand, costs a lot of money and can execute billions of instructions a second. The I/O controller, I don't know, maybe does 100 instructions a second or something. And that load, when you issue the load, it stalls the CPU until the answer comes back. So it's something to keep in mind when we talk about this. So it's really quite slow, but it works. And it's the basis of all communication with I/O controllers. So, we're not done. We have a problem. And the problem can be illustrated by the mouse. So let's say I'm talking to the mouse, and I'm the CPU. Do I need to know when the mouse moves? Yes, why? I have a little pointer, right? mouse moves, you expect the pointer to move. Now that's not magic. That's the trackpad, but the trackpad's not doing that. The CPU is a program running on the CPU that's moving the location of the mouse on the screen, so it needs to know where the mouse is. So using programmed I/O, how would I do that? Well, I would send I would issue a load from the mouse, and I would get back either a 0 or 1, for example, indicating whether the mouse has moved since the last time I'd asked. Or maybe I would get back, something else. Let's say it's 0 or 1. So 0, the mouse hasn't moved. So I do this. Now, how often do I need to do it? Pretty frequently, right? So has anybody ever used a system where you move the mouse, and then a little while later, you move it? Yes, right? No, that's not fun, right? This is an illusion that I'm actually touching the screen. It has to register very quickly. So I may have only a few milliseconds of delay. So let's say it's 10 milliseconds. So I have to ask the mouse every 10 milliseconds, have you moved? And what does the mouse usually say? No. So it's like, have you moved? No. Have you moved? Move. Move again? Constantly I'm asking, every 10 milliseconds. And every time I'm doing this, I'm using this really slow load. Slowing down this expensive CPU just to ask the mouse, have you moved? Bad. We won't do that. The other reason that this program down, the other way it's not good, is if I want to transfer lots of data from an I/O controller. Let's say I'm reading from a file, and I'm going to read, say, 16 kilobytes of data into a buffer that I've allocated with malloc. Now, where is that data going to go in this picture? Well, in the picture in the previous slide. It's going to memory, right? But if I use programmed I/O to get it, what I would be doing was say, okay, the I/O controller say, oh yeah, I got something for you. So now, okay, give me the first 8 bytes, because I can ask for 8 bytes at a time. Give me the first 8 bytes. All right, got those. Now send them to memory. And the CPU asks, okay, now give me the second 8 bytes. Okay, got that. Send it to memory. Give me the rest. And so for this entire time, if you think about the time that's involved here, the CPU is sitting there waiting in the slow load to get data from the controller. So that's bad. If it's just a little, a couple times it does, it's okay. But for 16 kilobytes, it's crazy because the CPU doesn't need to be involved at all. So we have solutions for both of those problems. Skipping over this. That just explains the polling with program data. I want to get to this. So, first thing we're going to talk about is, I'm going to do the bottom one first, interrupts. So, the idea of an interrupt is we're going to give the power to an I/O controller so that it can send a message to the CPU. Now, this message doesn't contain any data. It's just, think of it as a doorbell. The CPU has a doorbell. Any of the I/O controllers can ring the doorbell. The doorbell is like a Google Nest doorbell, has a camera on it. And the CPU can see who rang the doorbell, but nothing else. Right? So what will happen in this example is when the mouse moves, the mouse will go ring the CPU's doorbell. The CPU will now know, oh, something happened at the mouse. Okay? That's the purpose of the interrupt. We'll see later, next class, that what this will cause something called an interrupt handler code to run, which would eventually, in the operating system, be part of that device driver. That would then go and say, okay, mouse, tell me what happened. Okay? So interrupts. Initiated at the I/O controller and interrupts the CPU to get its attention. Solves the polling problem, the first problem. The other problem is solved by giving I/O controllers direct access to memory. So they can transfer big chunks of data to memory or from memory, any location in memory, without the CPU being involved. So, like in the case of the disk read, the CPU would use, and we'll see this in an example, we'll use programmed data to say, tell the disk, okay, look, get this data, and when it's all done, put it in this buffer. A couple programmed IOs, and then the CPU's done. And it moves on and does other things, and in the meantime, you know, data will be transferred into memory from that out controller without the CPU being involved at all. Okay, so the big picture here is programmed I/O. The star means where it can be initiated. It can only be initiated by a program running on the CPU, and can be used to send data to or receive data from the out controller. It has high overhead, and so should be used sparingly. Not for polling, not for bulk transfers. Then we have DMA. DMA is always initiated at an out controller, and it's used to send data in bulk directly to memory or get data in bulk from it. In parallel with the CPU is doing, without involving the CPU at all. CPU is running one program while this is doing the transfer. And then we have interrupts that are always initiated at an IO controller, and they give the IO controller a way to tell the CPU to pay attention